Section 6.1, greatest common factors and factoring by grouping. In the last chapter, chapter 5, we dealt with polynomials. We talked about adding them and subtracting them and multiplying them and dividing them. We talked about our power rules. We talked about all of that. Now, those power rules are never going away. What we're going to be doing in chapter 6 is we're going to be factoring. Now, what does it mean to factor something? It means that you're going to rewrite the problem as a multiplication problem instead of an addition or a subtraction problem. You can think of factoring as unmultiplying, okay? Now, you might be wondering why you need to learn how to multiply something and then you have to learn how to undo it. They both have very specific uses, and you will see that when we get to where we are solving equations using these things. Right now, we're just building up the skills we need in order to get to where we can solve equations with these. Okay, now what you will find if you look at under the notes section, or sorry, the files section in Blackboard, is you will look and you will find within chapter 6, you will find a factoring guide. Now this is a flow chart. It is not beautiful. I'm going to keep working on this to make it look better, but everything you need is here. Now, so later if you look at it, it looks a little bit different. It's just I've made it look better. I haven't fundamentally changed everything. So this will help you talk your way through how to factor, and it's not nearly as complicated as it looks right here, okay? The first thing we want to talk about is the greatest common factor, which we often call the GCF. And this is the largest thing that divides evenly into every single term we have. So if we're looking at 15y minus 60, we want to rewrite this as a multiplication problem, okay? And we want to find the largest thing that divides evenly into 15y and also 60. The largest number that divides into both, our GCF, is going to be 15. 15 divides evenly into 15y. 15 also divides evenly into 60. So what we're going to do is we're going to rewrite this as a distribution problem. And we're going to write 15 on the outside. And then think about what we would have to multiply by in order to get back to here. 15 times something gives you 15y, and that's going to be y. 15 times something is going to give you negative 60. And that's going to be a minus 4. Okay? Now think about this going backwards. 15 times y is 15y. 15 times negative 4 is negative 60. Okay? Now you want to double check that this is the largest thing you could factor out. Just make sure there's nothing that divides evenly into both y and negative 4, and you have this thing totally factored. Now, I said make sure that you factor out the largest thing. So let's look at real quick at what happens if you don't pick the largest GCF. For example, 15 and 60, these are both divisible by 5. So let's do that. Let's say that I think my GCF is 5, and so I factor out a 5. 5 times what gives me 15y? Well, that would be a 3y. 5 times what gives me negative 60? That would be a negative 12. And then look at this, okay? Well, 3 and 12, both of those are still divisible by 3. So what that tells me is I did not pick the largest thing here. You don't have to start all over again. All you can do is like say, okay, well, that's 5. Now let's say I factor a 3 out of this. So I'm kind of pretending that 5 isn't there anymore. 3 times y gives me 3y. 3 times a negative 4 will give me the 12. And then if you multiply these two back together, you get the 15. So all is not lost if you didn't find the greatest common factor on your first try. You just have to keep double checking to make sure that you have factored completely. Now, all of the problems in chapter 6, you're going to be asked to factor completely. And that means you're always going to need to be looking at what you have left and making sure that you have done absolutely everything possible. Okay. So let's look at 9z to the 4th plus 27z. This time I have a variable in both of them. In order for the variable to be part of your GCF, it needs to appear in every single term. I said every single, here we have 2, here we have 3, we can have a bunch more. As long as the variable is in every term, you're going to have a variable in your GCF. Okay? Let's deal with the number part first. 9 and 27, these are both divisible by 9. 9 is the largest number that can possibly go into 9, so that's our GCF. Okay, now look at our variables. There's a z in both of them, so I'm going to have a z here. Now the only thing we need to check for now is what exponent to use on that z. What you want to do is you want to look at every single term and then use the smallest exponent. Okay, so I have a 4 exponent here, and this is a 1. So since this one's smaller, I just use 9z as my GCF. So if I factor this, I'm factoring out a 9z, and now I want to write what I need to multiply here to distribute by. 9z times what gives me 9z to the 4th? That will be a z cubed. 9z times what gives me 27? Z, that would be a 3. Double check that nothing factors out of both of these, and you're good. Notice that the language I'm using to figure out what needs to go inside the parentheses here is exactly the same language I was using when we did long division. This times what gives me this. So we are doing the same type of thinking we were using when we were using long division. Okay, so let's try this one. I have an 18, a 36, and a 48. So I need to find the GCF of those numbers. And then I have a k in each of these, so I'm definitely going to have a k in my greatest common factor. My GCF is going to be, okay, so I look at these two. 18 and 36 are both divisible by 9, but 48 is not. So 9 is going to be too big. 6. If I can divide this by 6, and this by 6 as well. So I think 6 is going to be my GCF on the number part of it anyway. And if it's not, we can make an adjustment just like we did up here. Okay. Now I do have a k in each of these, so I'm going to have a k here. And then I use the smallest exponent. So my smallest exponent is a 3, so I'm going to use a 3 here. Okay, so this factored. I'm going to factor out a 6k to the 3rd power times. This times what gives me this? Well, the k cubed is already correct. 6 times 3 gives me the 18, so I'm going to put a 3 here. Okay. 6 times what gives me 36? Well, that would be a 6, negative 6. So minus 6. That's still going to have a k cubed here, and I need k to the 4th, so I need another k here. Okay. Now plus 6 times 8 gives me 48. Here I have 3 k's, here I need 5, so I'm going to need another 2. So k squared there. Okay, so I think maybe this is my answer factored. I'm going to do a double check to make sure nothing else will come out. Of these two, I could factor out a 3, but I can't do that here. Here I could factor out a 2, but I can't here. There's nothing that goes into 3, 6, and 8. So 6 is the largest number. This one doesn't have a k, so this was the largest k value I could factor out. This is my answer. Now you'll notice here that this is not in the quote-unquote correct form. So your better answer would be like this, to put them in descending power order. The computer is less picky about this in this chapter, but still, this is your better answer. Okay, so let's check out this one. Negative 50 r to the 4th t squared plus 81 x cubed y cubed minus 48 p squared q to the 4th. Okay, so let's look at these numbers. I'm just going to cover up this one. I'm going to see if I can find a number that will work for these two, and then I can check it out here. Okay? So 50, things that divide into 50 would be a 2. That doesn't go into 2 here. A 5, not a 5. A 10, no. A 25, no. Everything that could possibly go into 50 is either some version of a 2 or a 5 multiplied together. In fact, 50, if you think about it in prime factorization terms, 50 is 2 times 5 times 5. Okay, so things that divide into 50, I'm ignoring the sign here, would be 2 times 25, 10 times 5, 10 times 5, that's just about it. And none of that goes into 81. 81, in fact, if you do a prime factorization of 81, that's 3 times 3 times 3 times 3. And if you look at the prime factorizations, you can see that they have nothing in common. Now, you do not have to do this every time. It will, it helps, but it's not absolutely necessary. One other trick you can use, and I want to stress that this is not the way to get this done, but if you're ever not sure if there's a number that divides into both of them, you can put it in as a fraction. If I do 50 over 81, and then I hit enter, and it reduces, that means there's some number that divides into both of them. But it didn't reduce. That tells me that the only thing that divides into 50 and 81 is a 1, so nothing factors out of those two as far as the numbers go. And if there's nothing I can factor out of these two, then there's certainly nothing I can factor out of all three. Okay, so nothing on the number front. Let's check out the variables. I would have to have the same variable in all three of them. Just start here. Here I have an R. There's no R here, no R here. Okay, so no R. The T, there's no T here, there's no T here. So not only is there nothing I can factor out of the numbers, I don't have a variable that appears in all of them. Okay, in this section, they say it cannot be factored. Okay, now there is one thing I want to stress here, and this comes to this factor tree, and I know we don't know everything about it yet, but our first step when we start factoring is to find the GCF if we have one. Okay, here we did not. We would go through this whole process here, and then at the very end, we would be asked if we were able to use any of these methods to solve, and of course, we don't know these right now. Our answer would be no, and so we would say that we have a prime polynomial. Prime numbers are only divisible by themselves and 1, and a prime polynomial is more or less the same thing. It's not equally divisible by anything. So later, we're going to say that this is prime.